The violent collisions that made life possible on Earth. Planetary systems are born from chaos. Clouds of gas and dust collapse under gravity, forming stars surrounded by swirling disks of material. Within these disks, tiny grains collide and stick, growing into rocky bodies called planetesimals. Over millions of years, these fragments merge into protoplanets, the building blocks of worlds. But according to new research, the final, most violent stage of this process, the last 1% of planetary growth, may have been the key to determining which planets could sustain life. If you like my content and want to listen more interesting science stories like this, then subscribe my channel and don't forget to like, share this video with your friends, relatives, and colleagues to spread the knowledge. A team led by the Southwest Research Institute, SwRI, in collaboration with Yale University, has reviewed decades of research on the early histories of Mercury, Venus, Earth, and Mars. Writing in Nature Reviews Earth and Environment, they argue that late-stage planetary collisions not only reshaped the inner solar system but also laid the foundation for planetary diversity and habitability. Earth versus Venus divergent fates. The study highlights the contrasting fates of Earth and Venus, two planets of similar size and composition that ended up with dramatically different environments. Using large-scale impact simulations, researchers found that Venus likely experienced higher energy collisions than Earth. These impacts superheated its core, driving prolonged volcanism and resurfacing events that erased much of its ancient history. By contrast, Earth's late collisions delivered not just energy, but also volatile rich material such as water. These impacts modified its atmosphere, influenced plate tectonics, and created conditions favorable to life. Earth may have been the last terrestrial planet to form, reaching 99% of its mass between 100 million years after the solar system's first solids condensed. That extra time, combined with the nature of its collisions, may have tipped the balance toward habitability. Why the last 1% matters lead. Author Dr. Simone Marchi explains, we examined the disproportionate role late accretion plays in shaping the long-term evolution of terrestrial planets. Even though it accounts for just the final 1% of growth, these late impacts can explain why planets with similar origins developed such distinct properties. Meteorite chemistry, lunar cratering records, and mantle geochemistry all support the idea that collisions were central to planetary evolution. They affected everything from crustal thickness and tectonic regimes to atmospheric loss or enrichment. Mars' patchy surface, Mercury's unusual metal-rich core, and Earth's water and tectonics can all be traced back, at least in part, to the legacy of late-stage bombardments. Implications for exoplanets. Understanding this violent chapter of planetary history is not only about explaining our solar system, it also guides the search for life elsewhere. The habitability of a rocky planet depends heavily on its atmosphere, which is shaped by tectonics and mantle outgassing, Marchi notes. These, in turn, are influenced by a planet's collision history. This means that when astronomers search for Earth-like exoplanets, they should look beyond simple metrics like mass, radius, and orbital zone. Two planets may be superficially similar but diverge dramatically in habitability, depending on whether their late growth brought stabilizing volatiles or stripped their atmospheres away, reconstructing the record of bombardment. Piecing together this history is difficult. Geological activity erases much of the evidence, particularly on Earth and Venus. To compensate, scientists rely on lunar craters, impact simulations, and geochemical tracers such as siderophile, iron-loving elements. These clues reveal how impactors delivered or removed volatiles like water and carbon, key ingredients for life. In some cases, collisions stripped atmospheres bare. In others, they delivered vast reservoirs of volatiles. For early Earth, the balance of these processes almost certainly influenced prebiotic chemistry, the chemical foundation for life itself, even if the exact pathways remain uncertain. Violent beginnings, fragile outcomes. What emerges is a picture of planetary formation as a precarious process. A world's destiny, lifeless like Venus, arid like Mars, or vibrant like Earth, may hinge on a few catastrophic impacts during the final sliver of its growth. As Marchi emphasizes, these processes almost certainly played a role in the prebiotic chemistry of early Earth, but their implications for the actual origin of life remain a mystery. The research underscores that planetary habitability is written in collisions, in the fiery impacts that built worlds, shattered them, or made them capable of hosting oceans, atmospheres, and ultimately